DAC. DAC means digital to analog converter, which has a step size of 10 millivolt, determining its full scale output voltage and percentage resolution. So, what is DAC means? DAC is a digital to analog converter, and they are asking about full scale output voltage. So, what is full scale output voltage is for 10 bit, the minimum value is 10 zeros, right? The minimum value of 10 bit is 10 zeros. So, what is the maximum value of 10 bits? Maximum value of 10 bit is 10 ones, right? So, 10 1 is a maximum value. Okay. So, 10 1 is your maximum value. So, what is this value? This is 1, 2, 4, 8, 16. Okay. So, if you add this one, you will get 1023. Okay. So, this is for this value, what is your full scale output voltage? We have to find. Okay. So, formula for percentage revolution is that is equal to 1 divided by total number of steps into 100. Okay. There is one more formula you have, step size divided by full scale voltage into 100. Okay. So, they have given the step size as 10 millivolt. So, 10 millivolt divided by full scale output voltage is that is equal to, formula is 2 power n minus 1 into 10 millivolt. Okay. So, to solve this one, so 10 millivolt get cancelled, then you will get 100 divided by 1023, right? Because n is equal to 10 bits. Okay, n is equal to 10. So if I substitute 2 power 10 is 1024 minus 1 is 1023 into 100. So what is the answer? What is 100 divided by 1023? 100 divided by 1023 is 0.097. Okay. Next, full scale output voltage. Full scale output voltage. Full scale output voltage is the denominator value. Okay. So what is the denominator value? Denominator value is 2 power n minus 1 into 10 millivolt. Okay. So 1023 into 10 millivolt. Okay. So answer is 10.23. Right. 10.23 volt. So next 97th problem. So here we are given a DAC which will produce an output voltage. So DAC is digital is my input and analog is my output, right? So for the digital input, digital is 5 bit input. Okay, maximum value of 5 bit is 5 ones, right? So this is your digital value. Analog is your output, right? So so for this analog, we know that analog voltage is equal to K into K means resolution. Okay, A is equal to, that is analog voltage is equal to resolution into digital input into gain. This is your formula. Okay, so here gain and all they haven't given. So what is the digital input? Digital input is 0001. So what is 001? That is 1 volt, right? So 1 into K. So I mentioned resolution as K. So this is your output, right? output is nothing but analog voltage, that is 0.2. So from this one I can find what is k. What is k? K is equal to 0.2. So after that they are asking about that full scale for the 5 ones. For the 5 ones, what is the for the 5 ones, that is digital input, what is my analog output? Okay, so V out is equal to, we know that k is resolution 0.2 into what is 5 1 is nothing but 31. Okay, that is 1 plus 2 4 8 16. So if you add this value, you will get 31. Okay, so 0.2 into 31 is 6.2 volt. So next 98. So here they have given for the digital input what is the full scale output of the same DAC. Okay, so 110010. What is 110010? This is 2 4 8 16. This is 16. This is 32. So 32. If I add this one, I will get 50. Okay, if I add this one, I will get 50. So 50 into resolution. This is resolution. Okay, this is your resolution, and this is your analog output. Okay. But how to find this value? So instead of this, I'm taking this one as k. Okay, k into 50. So I'll get k is equal to 1 by 50. Okay. So what is analog output? Analog output is for full scale output they are asking. Okay, full scale output means for 8 bit, what is the full scale output? For 8 bit, 8 ones, right? So what is 2 1? What is 2 ones? It is 1 plus 2, that is 3, right? So instead of for 2 ones, you have to take like this. This is 2 power 2. What is 2 power 2? 2 power 2 is 4. Okay, so 4 minus 1 is 3. Okay, so likewise, what is 2 power 8? 2 power 8. What is 2 power 8? 2 power 8 is 256. So if you subtract minus 1, you will get this is 255. Answer is 255. Okay, so for 50, I am getting the analog input voltage, analog output as 1. Okay, so for 255, what is the analog output? This is what the question. So 255 divided by 50, you will get 5.1 volt. This is your answer. Next 99. So a pulse time with the frequency of 1 megahertz is counted using a mod 1024 count, 1024 ripple counter. So they have given it as a ripple counter. Ripple counter means it is a asynchronous counter. Okay, so what is mod 1024? Mod 1024 is 2 power 10. What is 2 power 10? 2 power 10 is 1024. Okay, so you require nearly 0 to 1023 states. Okay, 0 to 1023 state is nothing but total value is 1024. So you require nearly 10 flip-flops. 10 flip-flops. Okay, 10 flip-flops to construct this 10 JK flip-flops. Okay, JK flip-flops to construct this ripple counter. Okay, so they have given the total frequency is 1 megahertz. Okay, so they are asking for per stage, per flip-flop stage, what is the propagation delay? So for the entire flip-flop, it is 1 megahertz. For one flip-flop, what is the your propagation delay? Okay, so we know that frequency is equal to 1 by t. Okay, So what is my t value? T value is equal to 1 divided by 1 megahertz, right? So 1 divided by 1 megahertz is 10 power minus 6 seconds. Okay, 10 power minus 6 seconds. So they are asking about for um, for so if you multiply this one, what you will get? This is in terms of 10 power minus 3. If I want to convert in terms of 10 power minus 9, I want to convert this. So I have to multiply by 1000 on both sides, right? 1000 on both sides. So I will get 1000 nanoseconds. Okay, this is your whole time period. Okay, this is for entire 10 flip-flops. So for each flip-flop means I have to divide it by 10, right? So if I divide it by 10 means I will get 100 nanoseconds. So this is your output. This is nothing but PMOS. This is a PMOS and this is your NMOS. Okay, and so this is P, this is N, and this is P. Okay, this is N, P, N, P, N. So whenever one conducts means another one is off in off state. Okay, so based on this input, based on the input of input value of P, either PMOS will conduct or NMOS will conduct. Okay, so if the input is 0 for the value of 0, the value of P is 0, what will happen? NMOS, this PMOS will conduct. Okay, for P is equal to 0, NMOS will conduct. PMOS will conduct. PMOS will conduct. Okay, when P is equal to 1, okay, I'm talking about this P. Okay, P is equal to 1, NMOS will conduct. Okay. So for P, Q, if it is 0, 0, 0, 1, 1, 0, 1, 1. What is my Y? Okay. First, we will assume P and Q is equal to 0, 0. If this is 0, which one will conduct? PMOS will conduct, right? PMOS will conduct. So this Q value will reach the output, right? Because Q only it is connected to P. Okay, so it will reach the Y. So what is the value of Q now? Q is 0. Okay, for the next state, Q. Now P is equal to 0 and Q is 1. So what is the value of Q? It will reach the Y. Okay. Okay. So next, P is 1 and Q is 0. So if it is 0 means this is 1. Okay. So if it is 1 means NMOS will conduct, right? NMOS will conduct, and if NMOS will conduct means this 1 will reach the out. Okay. Next, 1, 1. So the PMOS will conduct. If PMOS will conduct means what happened? The circuit is like this. Okay. This is 1 and this is 0. So PMOS is conducting. So this is connected to Y. Okay. This is open circuit. Okay. This is open circuit area. So this is 0 now. Okay. So answer is XRD. Next. So this is nothing but 2:1 mux. Okay. This is a 2:1 mux. So what does mux means? This is many to 1. Many to 1. Why I am telling this is 2:1 means 1 mux means here n is my selection pin. Okay, n is my selection pin, and here I have only one selection pin. Okay, so if n is equal to 1, this is your selection pin. So you will get 2 is your input, this is your input, and this is your output. Okay, so always you have only one output for mux. Okay. So if the selection pin is if the selection pin is 0, Y will pass through this output. Okay. So if the selection pin is 1, this 0 will pass through the output. So this is your concept. Okay. So how to write this one? So you can write when when x is 0, okay, like in term this one as W. Okay, this is W. So what is W? W is equal to when x is 0. Okay, when x is 0, Y is selected. When x is 1, 0 is selected. Okay, so answer is x power Y. Okay, W is x power Y. What is F? F is when Z is 0. When Z is 0, W is selected. When Z is 1, W bar is selected. Okay. So what is W bar? W is x bar Y plus Z. So x bar Y whole bar. Okay. So this is equal to x bar Y Z bar plus Z into x plus, so applying a De Morgan's law, x plus Y bar. So what's the answer you are getting? X bar Y Z bar X Y bar Z X Z. Answer is B. Or not 2. So in DRAM, what is DRAM means? Dynamic random access memory. Okay, or random access memory. So here you require here in the circuit diagram is you have only one transistor and one capacitor. Okay, so this capacitor often will leakage the charges. Okay, So it requires some periodic refreshing in order to get full charge. Okay, so and if the charge is full means which means the value of this timing gram is 1. Okay, if there is no charge in the capacitor means the value is 0. Okay, so you see periodic refreshing is not required. So this is not your answer. Okay, the information is stored in the capacitor, right? The information is stored in the latch, it's not correct. So both the read and write operation can be performed simultaneously. So you can't perform the read and write operation simultaneously. So the information is stored in the capacitor is your answer. See here, this is a NOT gate. Okay, so this is P and this is P bar. Okay, so this is nothing but AND gate. Okay, AND gate. AND gate means multiplication of this one. So what is the multiplication of this one? P bar, Q bar, R. Right? P bar, Q bar, R. And what is this one? P bar, Q, R. Okay, and this one is P, Q bar, R. So which one is your answer? Answer is C. So what is F? F is in terms of sum of products. Here they have given A is your MSP and C is your LSP. Okay. So it is given, it is a sum of products. Sum of products, and you have 3 variables. So you have to draw the 3 variable table. So 3 variables totally you have 8 cells, right? A is your MSB. They have given A is the MSB. A is the MSB and C is your LSB. So they have given F is equal to M0 plus M2 plus M3 plus M5. So what is M0? M0 means 000, right? What is M3? M3 is 011. What is M5? M5 is 101. What is M2? 010. Okay. So you have to find where is 000. You have 000 here. So this is 1, 010, then 011, then 101. So how to group this one? So this is your first value, and this is your second value, and this is your third value. So what's the answer? This is A, B bar, C, and this one is A bar, B. This one is A bar, C. So what's the answer? A bar, C bar, sir. A bar, C. The answer is B. Next, 105. So they are asking what is phi. Okay. So this is your AND gate. So you'll get AB, and AB into C you will get ABC, and C into B you will get BC, and AB you are XORing with CB, right? So what is Y? Y is equal to now ABC XOR AB XOR CB. Okay. So you see, what is A XOR B? What is A XOR B? A XOR B is equal to AB bar plus A bar B, right? So now you substitute here. Okay. AB XOR CB. AB XOR CB is AB into CB bar plus AB bar CB. Okay. So I can write CB, the whole bar is equal to C bar plus B bar according to the De Morgan's law. Likewise, AB bar I can write it as A bar plus B bar into CB. Okay. So B into B bar is 0. So I will get AB C bar plus here also B into B bar is 0. So I will get A bar CB. Okay. So now this is in terms of so I can take this is X, this is Y. So X bar Y is equal to X Y bar plus X bar Y, right? So I can write ABC into AB C bar plus A bar CB the whole bar plus AB C bar plus A bar CB into ABC the whole bar. Okay. So again I am applying the De Morgan's law here. So I will get like this. Okay. So now, so if I multiply A into A bar, this is 0. Okay. So I will get A bar CB. Okay. If I multiply with this one. And B into B bar is 0 and B into B bar is 0. So B bar get cancelled out. And C into C bar is 0. So I will get only AB C bar. Okay. So likewise, here I am cross multiplying this 3 terms with this one. Okay. So A into A bar is 0. So A B bar I will get first A B bar. Next A into C is AC. Then C bar into A bar is A bar C bar plus C bar B bar. C into C bar is 0. And B A bar. Okay, B A bar. And B bar into B bar is B bar C. Okay. So here if I take B bar common in this whole term, if I take B bar common means I will get only B bar, right? I will get only B bar. B bar with anything else B bar. So this term totally get cancelled out. I will get only AC. Okay. So if I multiply AC with ABC means it is nothing but ABC plus this 2 terms. Okay. So in those 2 terms, if I take C plus C bar, what is C plus C bar? C plus C bar is 1. So I'll get AB plus A bar CB. And if I take B as common, I will get A plus A bar C. So A plus A bar C, I can write it like this: A plus A bar into A plus C. So I'll get A plus C. So answer is B into A plus C. B into A plus C is your answer. So here you have a decoder and you have some buffer. So this is called as tri-state buffer. Okay, tri-state buffer, because you're having 3 pins. Okay. So what is the actual output of decoder is if C0 is your input and you have 4 outputs, right? It's O02, sorry, O02, O3. Okay, if it is 00, I will get 1, 01, it is 1, O1 is 1, and 10 is O2 is 1, 11 is O3 is 1. Okay, so this is a output of a decoder, 2:4 decoder, and so okay, so you see, you are having, after that you are having only 4 inputs. Okay, you are having 4 inputs and you have only 1 output. Okay, so if C1 and C2 is 00, this O of 0 only gets selected and P will reach the output, right? P will reach the output. If it is 01, what happened? O1 is selected, O1 gets selected and Q will reach the Y, right? If it is 10, O2 gets selected, and because O2 value is 1 here, okay, so R will reach the output. So this is actually a 4:1 mux. Okay. So 107. 4-bit 2's complement representation of a decimal number is 1 1,220. Okay, I already told you the formula, right? 2 power n minus 1 minus this is a 2's complement number, 2 power n minus 1 minus 1. So this is a formula. Okay, so what is the 2 power n here? N is 4. Okay, so we'll get minus 8 to 7. Okay, so this value will ranges from minus 8 to 7. So if MSB is 1 means it is negative. Okay, so this is not your answer. Okay, so this also it is not your answer. So what does 1000 means? 1000 is 8, right? This is 8, so it is minus 8. If you take 1's complement of this number, 0, 1, 1, 1 plus 1. This is a 2's complement of this number. So 0, 0, 0, 0. Okay, this is minus 8. Okay. So they have given this is actually a 4-bit number, this is a 5-bit number, this is a 6-bit number. Okay. So here the MSB is 1. So it is a negative number, right? This is a negative number. So this is not your answer. Okay. So let us take 1001. So we will invert this number. So if I invert this number, I will get 110, adding 1 with this number. So I'll get 111. Okay. So what is this 111? 111 is nothing but -7. Okay. So from this one, I can identify this is my answer. This is my answer. Even you consider this number 21001. So you invert this number. You invert this number to get this. So this is nothing but -7. 111. So this MSP represents -7. You take the next number 11001. So if you invert this number, you get. So this is nothing but -7. No, not me. An equivalent 2's complement representation of the 2's complement number 1101. Okay. So what is 1101? 1101 is nothing but 1101. So what is this one? This is -2, right? -3. -3. Okay. So this is a negative number, right? So this MSP is negative. So this will not be your answer. And I need to get -3, right? So let me take this D. So if I invert this number, I will get -3. So D is my answer. Next, number systems. Okay. So in the number systems, usually you have 4 types. One is binary, next one is decimal, another one is hexadecimal, another one is octal. Okay. So the radix means base of this number is 2. This is 10 and this is 16. Okay, and this is 8. So why I am keeping the radix as 2 means for the binary number, it is having only 2 numbers. One is 0, another one is 1. Okay. So for a decimal number, it ranges from 0 to 9. So totally, I have 10 numbers. That is why the base is 10. Okay. So hexadecimal means it ranges from 0 to 9 and followed by A to H. Next octal. So here A represents 10 and H represents F represents 2. Okay. So octal, it ranges from 0 to 7. It ranges from the numbers 0 to 7. So what we are going to, what we learn from this one is, if the base is 8, if the base is 8, the number is not exceeding that base. Okay. So you can see here they have given 24. So 24 is not exceeding 5, right? 2 and 4 is not exceeding the 5. Suppose they are given 67 base 5. So this representation itself is wrong. Okay. So 2, 4 base 5. So 2, 4 base 5 is represented as 0, 1, 0 and 1, 0, 0. So how this number is represented in terms of base 5? Okay. So this is a question they are asking. So 2 is represented as 0, 1, 0, right? 2 is representing as 0, 1, 0 and 4 is representing as 1, 1, 0, 0. Okay. So likewise, I need to split the numbers in 3 bits. Okay, split this number in 3 bits. What is 0, 0, 1? 0, 0, 1 is 1. And what is 0, 1, 1 is 3. And what is 0, 1, 0 is 2. And 1, 0, 0 is 4. So which is my answer? 4, 2, 3. B is my answer. One, one, one. So here they are given Q and P. Q and P is denoted, represented in the 2's complement number. Okay, this 2's complement value of Q is this one, and 2's complement representation of P is this one. So they are asking if Q is separated from P. So you have to note down this question. Okay, Q is separated from P means that is Q minus P or P minus Q. That is P minus Q or Q minus P. It is P minus Q. Okay, so I have written P here. Then I have taken 2's complement of this number, because subtraction means you have to take 2's complement, then you have to perform the addition. So 2's complement representation of Q is, okay, I have taken inverse of this number, then I have added 1 with this number. So after 1, you have to invert rest of the numbers. Okay, so I have inverted the rest of the numbers. After that, I have added 1. Okay, so if I add 1 means I will get 1 followed by 5 zeros, 1, 1. Okay, so I can omit the carry now. So answer is 7. Okay, so in which place I am getting 7? So answer is B. So they are given 4:1 mux is used for generating the output carry of a full adder. So output carry of a full adder is AB plus BC plus CA, right? Yes, sir. output carry for the full adder. A and B are the bits to be added, while Cin is my input carry and Cout is my output carry. A and B are used as a selection bit, while A is a most significant bits. Which one is corrected? Describe now the choose of the signal to be connected. Input okay. So first we will write the truth table for um, full adder. Okay. So what is 0, 0, 0? 0, 0, 0 means carry 0. 0, 0, 1 means carry 0. 0, 1, 0 means carry 0. 0, 1, 1 means carries 1. 1, 0, 0 means carry 0. And 1, 0, 1 means carries 1. And 1, 1, 0 means carries 1. And triple 1 also carries 1. Okay. So now I'm writing in terms of 4 bits. Okay, this is I0, this is I1, I2, I3. So this is 0. So I'm writing this one. Okay, 0, 0, 0, 1. 0, 0, 0, 1. Followed by 0, 1, 1, 1. So it's not a K mark. Okay. So what is 0, 0? 0, 0 is 0. Okay. So I write this is C and this is C bar. Okay. So this is C bar and this is C. So if I group this one, I will get C. Okay. Likewise, if I group this one, I will C. C is nothing but C. Okay. And 1, 1 is 1. So what's the answer? Answer is A. You can also substitute this one and also C. Okay, what is C out? C out is equal to 0 into A bar B bar. 0 into A bar B bar plus C in into A bar B, right? And C into A B bar plus A B. Okay. So A B plus C in into A XOR B. So also one more formula you have A B plus C into A XOR B. It's another formula for carry. A signed integer has been stored in a byte using a 2's complement format. We wish to store the same integer in a 16-bit word. We should. So C is your answer. We'll discuss this one in the next class. Okay. 130. So given f of w comma x comma y comma z is equal to wy plus xy plus w bar xy z plus w bar x bar y plus xy plus x bar y bar z bar. Complete the set of essential prime integers. So first you have to draw the K-mark for this one. Okay. So if I draw the K-mark for this one, take W, X, Y, Z. So I have to write in this order. Okay, W, X, Y, Z. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. What is W, Y? Where you have W, so this is your W, right? This is your W, and Y you are having here, this two. So this is my WY, right? This is your WY. Next, XY. XY is here you have XY. Here you have XY, sorry, X. And Y is here you have Y, right? So you have to fill these two areas. Okay. So next, W bar X, Y, Z. So this is W bar. This is W bar X. Okay, this is W bar X. And Y, Z you are having here. This is my Y, Z, right? This is my Y, Z. Next, W bar X bar. So this is W bar X bar. Y you are having here. This 2 is Y. Okay, so I'm filling here. Next, X Z bar. So this is your X. This 2 is your X. X. So where is Z bar? Sorry, Z. Z is here. These two places. So filling here. Next, X bar, Y bar, Z bar. So X bar you are having here. This is your X bar. This is your X bar. This 2 is your X bar. And where is Y bar, Z bar? Y bar, Z bar is this one. Y bar and Z bar. Okay. So now I am going to group. How to group this one? So I can group this 8 ones. Then I can group this 4 ones. Then I can group this 4 corners, right? So these are my 3 essential prime impedance, right? These are my 3 essential prime impedance. So what are they? So if I group this one, just 4 ones, I will get X bar Z, right? And if I group this 8 ones, I will get Y. Okay. Then if I group this 4 ones, I'll get X Z. So answer is B. So they are asked to find Y. Okay. So AB means AB the whole bar. So this is a bar, so this is B bar. So we'll get AB the whole bar into B the whole bar, B bar the whole bar. So we'll get, so what you will get? AB plus B. So this is equal to B. If I take common, I will get 1 plus A, that is equal to B. Okay, so this is B. So this is B means this is B plus C bar the whole bar. And if this is B, this is also B. So B into B is B. So it is B bar. So this I can write it like this: B bar C. Okay. So the final answer is B bar plus B bar C, the whole bar. Okay. So if I take B bar common, I'll get 1 plus C, the whole bar, right? So this is nothing but B bar into 1, the whole bar. That is equal to B. B is your answer. So consider this is your light. Okay, this is your light. So this has to emit the light. This has to emit the light when both the switch are closed. Okay, this is what we need to identify. Okay, so basically the switch will work only when if I give positive to this one and ground to this one. So if it is 0 means the light will emit, the bulb will emit the light. Okay, so this is 0 means the bulb will emit the light. Okay, so if it is 0 means for what are the values it is 0? Only for the values it is 1 and 1, this should be 0, right? This is 1 and 1 only. One into 1. Okay, so if it is 1 means this is either 0 1 or this is 1 0. This is the case. Okay, so if this AND gate should be 1 means both the inputs should be 1. Okay, so if one switch is closed, means this will goes to 0. Okay, this will goes to 0, so this becomes 0. So S1 should not closed. Okay, so this will not be my answer. Okay, so consider both the switch are open now. Okay, both the switch are open. So both the switch are open means this is 1 1, this is 1 1. Now both the switch are open means this is 1, this is 1 1, right? Now both the switch are open, so it is 1 1, so I'll get 1 here, and I need to make this one as 0. Okay, so it is not possible, right? Here it is 1 already, so it is always 1 here. Okay, so it doesn't emit the light irrespective of the situation. This is your answer. still 160. Say the question is given like this. Y we are asking is y is equal to AB. So you have to multiply this two. Okay. So here this is nothing but AB, and here so what is this one? This y. This is 0 into B bar is equal to 0. So what is the answer? Answer is 100. The question is what is the minimum number of two input NAND gate which is required to implement a XOR gate. So you note on this formula. So if I want to implement a NAND gate, minimum number of NAND gate, minimum number of NAND gate, minimum number of NOR gate. Okay. So if I want to implement XOR gate means it will take 4 NAND gate to implement 4 NAND gate. Okay. If I want XNOR gate means it will take 5 NAND gate. Okay. So if you alter this two, you will get for NOR gate. If you alter this two, you will get for NOR gate. For NOT gate, only one is required. So what is the answer? What is the minimum number of NAND gate in order to implement XOR gate is 4. This is your answer. 4 is your answer. So the current state of QA and QB of two JK flip-flop is 0, 0. Okay, 0, 0. Assume the clock rise time is much smaller than the delay of JK flip-flop. What is the next state? Okay. So this is 1. So if it is 5 volt, 5 volt means JK both are 1. Okay. So both are 1 means it will act as a toggle flip-flop. Okay. Toggle flip-flops. So 0 becomes 1 now. Okay. So this 1 will reach this 1 means, so you will get the answer as 1. This is your answer. So this is 2:1 much. So what is the formula? F is equal to when it is B bar, it is A bar. Okay. When it is B, it is A. So this is nothing but XOR B. See, this is exactly opposite to that of that module problem, module 1024 problem. Okay, so they have given it is 4-bit. 4-bit means require 4 flip-flops, right? 4 JK flip-flops. Okay, so the propagation delay of each flip-flop is 50 nanoseconds. Means for 4 flip-flops, it is taking 200 nanoseconds for 4 flip-flops. So what is F? F is equal to 1 divided by T. So 1 divided by T means 200 10 power 9, okay, into 10 power 9. So what you will get? 10 power 7 divided by 2, right? So 5 megahertz. Yes. On 21. So here it is given both all the inputs for the flip-flop is 1. Okay, it is 1. So this is your MSB, sorry, this is your LSB and this is your MSB. And since Q is connected to this negative edge trigger flip-flop, it is nothing but it is a up counter. Okay, up counter. So it will count up to 00000 to 111. Okay. So, but here it gets stopped after this NAND gate. Okay. So, what is the where it is connected NAND gate? So, if I take this one as D, and this is C, and this is B, and this is K. Okay. So, this is QA, QB, QC, and this is QD. Okay. So, it ranges from 4 zeros to 4 ones, right? So 4 ones ranges from 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 2, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, then 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1. So what else? X, if I take this is X is equal to QA, this is QA, and this is QC, QA, QC, the whole bar. So this is equal to QA bar plus QC bar. So if you see up to this stage, okay, what is QA bar plus QC bar? It is 1. Okay, for up to this stage, QA bar plus QC bar is 1, right? So if I consider this one, QA bar plus QC bar is also 1. Okay, so this will reach here to this one, to this one. Okay, so here also QA bar plus QC bar is 1. So consider this state. QA bar plus QC bar is 0. At this stage, QA bar plus QC bar is 0. So I have to consider only this state alone. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So totally I'm having 10 states. Okay, so totally I'm having 10 states. So given input frequency is 10 kilohertz. Given input frequency is 10 kilohertz. We know that f out. They are asking f out. What is f out? F out is equal to f in divided by total number of states. So answer is 1 kilohertz. Next 122. So given sequential circuits using D flip-flops and logic gates as shown in the figure, X and Y are the inputs and C is your output. So this is a circuit is a flip-flop. So this is the bar, and this is X bar. So usually in the J flip-flops, you can see J is connected to Q bar. Okay, J is connected to Q bar and K is connected to Q. Okay, so if I consider Z is Q and Z bar is Q bar, the Q bar is connected to Q should be connected to K. So X should be K. Okay, next K bar. I can take this one also, K bar, and Q bar. Q bar is connected to G, so I can take this one as equal to J. So answer is X is equal to K and Y is equal to K. So it's a JK flip-flop with X is equal to K and Y is equal to J. See here, this is connected to, this is not connected to a bubble, so it is nothing but a down counter. Okay, this is a down counter. So what is so if I consider this is Q bar, and this is QB. Okay, QB, and this is QC bar. So I told you this is a down counter. So let me write down counter. So this is nothing but QA, and this is QB, and this is QC. Okay. So you have to check this should be equal to 1. Okay. When it will be 1? When it will be 1, it is when it is 0, 1, 0. When it is 0, 1, 0, it becomes 1. So before that and all, it is 0. Okay, before that and all, it is 0. You can multiply it and see. Okay, when it reaches 0, 1, 0, it goes to 1. So totally how many number of states are there? 5, right? So mod 5 down comes 124. A 2-bit binary multiplier can be implemented using a 6 2-input NAND gate and 6 2-input or XOR gate. So what is this one? This is X, Y, the whole bar. This is Y bar. This is Y bar, Z, the whole bar. Okay. So now what is F? F is equal to X, Y, the whole bar into Y bar, Z, the whole bar. So this is equal to X, Y plus Y bar, Z. Option. So given 4:1 mux with a Boolean function of x, comma y, comma z. So here you can identify this is nothing but my MSP. Okay. So the input y and z is connected to the selection pin, canonical sum of product. Okay. So how to write F? F is equal to when y and z is 0, 0. When y and z is 0, 0. Okay. X gets selected, right? This one will flow to the output. When this is 0, 1. 0, 1 means x, y bar, z. Y bar is at 0 will flow to the output. Okay. Next, y is at bar. X bar will flow to the output. Next, y is at 1 will flow to the output. Okay. So now I can write this one as, because x is MSP. Now x is MSP, next followed by y, next followed by z. So I am writing like this: y z bar, y bar z bar, plus 0 to 0 of anything is 0. Next x bar, y z bar. Next y z. So what is 1? 1 is x plus x bar. I can write x plus x bar because here x is missing. Okay. So if I multiply this one, I will get x, y, z plus x bar, y, z. Okay. So this is equal to 100 plus 010 plus 111 plus 011. Because bar means 0, if there is no bar means it is 1. So what is 100? 100 is 4, right? Plus 2. This is 2, and this is 7, and this is 3. So 2, 3, 4, 7 is my answer. So here it is given it is a sum of product. Okay. So this is sum of product. So that it is this is nothing but sum of product, and this is nothing but mean terms. Anyone try to answer this problem? I already told you here A is equal to J because J is connected to Q bar, and here B is nothing but K. So what is the characteristics table for JK flip-flop? Is 0 0 0 1 1 0 1 1. There is Q 0 1 and Q bar. Okay. So given it is 1 0. Okay. So 1 0 means output becomes 1. Okay. If Q is 1, Q bar is 0. The answer is 1 0. They are asking output is Q bar. Okay, Q is 1, Q bar is 0. So what is a decimal representation of that? Number 27.625. Okay, base 2. So first you have to take this number 27. 27 you have to divide it by 2. Okay, so you get 1 3. So 13 into 2 is 26. Remainder 1. Next 2, 6. 6 into 2 is 12. Remainder 1. So 3 into 2 is 6. Remainder 0. 1 into 2 is 2. Remainder 1. Okay, so answer is, you have to write in this way: 1 0 1 0 1 1 1 1 0 1 1. Okay, next you have to take 0.625. Okay, because it is 27.625. Yeah, 27.625. Already we have taken 27. So the rest of the number is 0.625. So you have to multiply it by 2. Okay, so if I multiply it by 2, I will get 0 1. 2 into 2 is 4. 4. And 6 into 2 is 12. Okay, so next you have to take 0.24. 0.24 should be multiplied by 2. Okay, so we'll get 84.0. Okay, into 2. So we'll get 6.0. 0.96. So again you have to multiply by 2. Five. 5. 5. This 5. So if I multiply this one, I will get 0.50. Okay. Again, if I multiply by 2, I will get 1.0. 1.00. So you have to stop when after the point digit. If you have 0, 0, 0, 0, you have to stop. Okay. Then you have to consider only this number. Okay. So my answer is 0.101. 0.101. This direction you have to. Okay. The answer is C. The question, number of comparator which we are required for implementing the 8-bit 8-bit flash analog to digital converters. So answer is 2 power n minus 1. Okay, this is your formula. So what is 2 power n minus 1? Here n is 8. So what is 2 power 8 minus 1? That is 2 power 8 is 256. Then minus 1, you will get 255. So given the number is POS. Okay. So POS, it is a 3-variable schema. Okay. It is a 3-variable schema. A, B, C. Okay. Otherwise you can write like this: 0, 0. This is 0, 0, 1. And this is 0, 1, 1. And this is 1, 0, 0. And this is 1, 1, 1. Okay. So what are the rest of the things you have to make 0? So 0. This is 2. This is 2. And 4 already there. So it is 5. Then it is 6. So this is your answer. So you don't need a schema to plot this. Because that is nothing but pi m of sorry, pi m of 1, 3, 4, 7. This I can also represent it as summation n 0, 2, 5, 6. So this is your 0, 2, 5, 6. So this is a synchronous counter JK flip-flop is shown in the figure. So what is the output sequence when it is started with 0, 0? Okay. So what is the formula for JK flip-flop? 0, 0, 0, 1, 1, 0, 1, 1. This is Q, 0, 1 and Q bar, right? So first, this flip-flop. Let me take this one. So here J is equal to 0, right? J is equal to 0 and K is equal to 1. So it will Q will remain the same state. Okay, Q will remain the same state. And for the next flip-flop, J is equal to 1 and K is equal to 1. Okay, so it goes to 0, 1, right? So obviously this 2 is my answer. The next state 0, 1. Okay. Plus 0, 1 means this is 1 and this is 0. Okay. So what is J is 1 and Q bar also 1. Okay, so this will goes to 1. Okay, this will goes to 1. So 0 will move to 1. Next, J is 1 and K is 0 plus 0. 0 plus 0 is 0. So 1, 0. This is also moving to 1. Okay, so my answer will be this 2. Okay, so now consider this is 1, 1. So this 1, 1 means this is 0. Okay, this is 0. Obviously, this is my answer, but I don't know which one is. I'm also moving for the next state. Okay, so this is 1 and this is 0, and for this one, this is 1, this is 1, and this is also 1. So my 1 will move to 0, and if it is 1, 0, it will remain in 1, 0. So C is my answer. So what is X bar Y? What is X bar Y plus XY bar? It is nothing but X NOR gate, right? What is this one? This is X NOR gate. This is XOR gate and this is X NOR gate. So first let me multiply this one XY the whole bar, right? So this is nothing but X bar into XY the whole bar. And what is this one? Y bar into X bar Y bar the whole bar. So this I can write it as X plus XY. This I can write it as Y plus XY. Okay. So if we take X common, I will get x. If I take y common, I will get y. Okay. So this is x, this is y. So answer is f is equal to x, y whole power. So then some mistake. Y bar வராதுல்ல. Okay. So here I can write x bar plus x and y plus x bar. This is equal to y plus x bar, which is equal to x y bar the whole bar. Okay. So here I can write it as x bar y and y bar plus x. So this is equal to y bar plus x and this is x bar y the whole bar. Okay. So what is now f? F is equal to x y bar the whole bar into x bar y the whole bar the whole bar. So this is equal to x y bar plus x bar y. So this is nothing but x bar. Option A is your option. So here you can see this NAND gate. With the help of NAND gate only, I have implemented the 2:1 2 input XOR gate. Okay. So how many NAND gate are required to implement the 2 input XOR gate means option is 4. Let's see how to implement 2 input XNOR gate. We can also see how many NAND gate are required to implement the 2 input XNOR gate. Okay, we will check. So what is minimum number of 2 input NAND gate required to implement XNOR gate? So we know the option is 5. Let's check how. So XNOR gate output is x bar y bar plus xy. Okay, so this is x bar plus y bar x xy, and this is xy. So for this one, with the market. So I already told you for AND gate you have to for the output you have to add 2 NOT gate. For OR gate you have to add 2 NOT gate at the input. Okay. So first let me add 2 input for 2 NOT gate at the output of the AND gate. So I have done. Okay. Next you have to add 2 NOT gate at the input of the OR gate. So we added 2 NOT gate at the input of the OR gate. Okay. So this is nothing but one NAND gate, and this is nothing but another NAND gate, and this is another NAND gate. Okay. So what is this one? Okay. If the input is 0, this is output is 1, and output is 0. Yeah, again, similarly for 1, the 0, so it is 1. So this is similar to a straight line. Okay. So straight line, so I can replace this one by a straight line, right? I can replace this one by a straight line. So how many NAND gates are required? 1, 2, 3, 4, 5. So total 5 NAND gates are required to implement. It's not. Suppose the question is what is the minimum number of 2 input NOR gate. NOR gate is required to implement XNOR gate. So we know the answer is 4. Okay. Let's check how. Okay. So I have to do in the reverse manner. Okay. So for the input of the AND gate, to add 2 inverter. And for the output of the OR gate, you have to add 2 inverter. Okay. So if I group this one, this is nothing but NOR gate. Okay, there is no use in drawing this one. So you can see 1, 2, 3, 4. Okay, 4 and gate is required. Okay, you have to apply the same in the same way. You have to how I have drawn, how I drawn for the two input NAND gate for XOR gate. Yeah, NAND gate. How many minimum number of two input NAND gate is required to implement XOR gate கேட்டாங்க. அது 4 வந்துச்சு இல்லையா? ஸோ அதே மாதிரி நீங்கள் இந்த டயக்ராம் நீங்கள் வரைஞ்சிருக்கோம் சரியா? நீங்கள் பார்த்தீங்கன்னா ப்ரிப்பேர் நியர்லி 1, 2, 3, 4, 5, 6 காமிக்குது இல்லையா? ஸோ நீங்கள் இந்த மாதிரி பிளாட் பண்ணிங்கன்னா ஸோ வந்து செக் பண்ணி பாருங்க. You get x bar, y bar plus xy. Let's check this one also. X plus y the whole bar. And this is x plus y bar the whole bar. What is this one? Y plus x plus y bar the whole bar. Okay. X plus x bar y bar the whole bar. This is equal to x plus x bar into x plus y bar the whole bar. This is equal to x plus y bar the whole bar. Similarly, y plus x bar y bar is equal to y plus x bar the whole bar. Okay. So now I can write this one as x bar y. It is nothing but x y bar. So what is f? F is equal to x bar y plus x y bar the whole bar. So this is nothing but x plus x XOR y. So it is nothing but x XOR y. So from this, the minimum number of minimum number of NOR gate to implement XOR gate is 4. Consider the Karnaugh map. Karnaugh map means K-naught. Okay. Where x denotes don't care, blank denotes 0. So the blanks and all it will denotes 0. Okay. So A, B, C, D are the inputs, and the A bar, B bar, C bar, D are the complements. So the above logic is implemented using two input NOR gate only. What is the minimum of NOR gate required? So if I group this one, I will get C A bar. Okay. So C A bar mean A bar C. This A, this C. So my F okay. So what is the minimum of NOR gate? NOR gate ni kettanaala so this is one NOR gate and there is no use of this two. So minimum you require two NOR gate to perform because this is AC, this is one NOR gate and this is another NOR gate. This NOR gate I can replace like this. Okay. So AC. So this is C bar. So A plus C bar the whole bar is equal to A bar C. So require two NOR gate in order to implement it's to 134. So they are given T flip-flop is connected to D flip-flop and both are initially set to 1. What is Q1 after third clock cycle or 1 1 and after fourth cycle or 0 0. We get down. So yeah. So initially Q1 and Q0 is 1 1. Okay. So if I apply the first clock cycle, okay. If T is 1 means Q1 get toggle. Q1 is equal to toggle. Toggle means inverted. So yeah. So Q1 enna value irukko? Q1 value Q1 is nothing but D. Yeah. Q1 is connected to D. So that will reach Q0. Yeah. Clock கொடுத்தோம்னா என்ன ஆயிடும் இந்த Q1 இருக்கிற வேல்யூ தான் வந்து Q0 போயிடும் சரியா so Q1 value will reach the Q0 the next clock cycle so Q1 value வந்து Q0 க்கு போயிடும் Q0 ல என்ன வேல்யூ இருக்கு 1 இருக்கு so 1 இருக்கறனால இந்த ஸ்டேட் வந்து Q1 ங்கற வேல்யூ Q1 ங்கற ஸ்டேட் வந்து it will invert okay so second clock cycle என்ன ஆகும் 0 வந்துரும் ஏனா Q1 will reach Q0 and திருப்பியும் இங்க 1 இருக்கறனால இந்த ஸ்டேட் வந்து toggle ஆயிடும் ஓகேவா so third clock cycle third one வந்து this will 1 so 0 ங்கறனால என்ன ஆயிடும் என்ன வேல்யூ இருக்கோ அதே தான் இங்க ரிமைன் ஆயிடும் so since it is 0 so இங்க 0 ஆ இருந்துச்சு அப்படினா Q1 ல என்ன வேல்யூ இருந்துச்சோ அதே வேல்யூ தான் இங்க பிரசன்ட் ஆகும் சரியா so next fourth clock cycle 1 becomes 0 இல்லையா 1 ங்கற வரனால fourth cycle so third clock cycle என்ன third clock cycle ல 1 1 fourth clock cycle ல 0 1 so answer is B okay so I hope you have understood something in the structure we will discuss the rest of the topic in the next class so thank you for your patient listening Thank you, students. So you can leave the class now. So if you have any doubt, you can ask.